Welcome to your next tutorial on linked lists where we dig a little bit deeper. So for this tutorial you will find all of the code in the Tut9 directory in the course library folder. So home library comp 1633 tutorial/tutorial 9. So this code contains a makefile and separate compilation and a full solution for all of the coding questions that you will find in this tutorial. So your first step should be to copy it over. Here, cp -r, everything else, copying it to your current directory that you want to work in, and then you'll have tutorial 9. In here you will find list.cpp and list.h. This contains everything for a linked list code that's just with integers. You have tutorial 9.cpp, which will contain everything about the main and running the program. And then wordlist.cpp and wordlist.h contain everything for a linked list of actual C strings. And you have your usual makefile that you can use to actually compile and run the entire program. So I've set this up once again for easily run-in changes during the tutorial. So the targets, we have all of our actual sources, and when I go to compile it by default, it will compile everything, clear the screen, and then actually run the program. Otherwise, you've got your normal cleans, and the generic rule is always at the bottom for converting your .cpps to .os to make for easy new makefiles. Now the first time you compile this, it will not actually run properly. It will go through everything in the very beginning and then crash, and this is due to the first question. Just be aware of it when you compile. It is supposed to crash in the beginning, and then we will actually be fixing this within the actual program itself. So the solution code you have does not have the actual fix in it. You'll have to follow along with the video and also fix it. So we have to assume that we have the struct node right here of the node pointer, similar to what we've had in the previous tutorial. And so I've opened up all these separate 4 windows to make it easy so I can have tons of the code up. I will keep the compilation up in this top window and then start opening up the rest of the files as we see here. So at the bottom I'm going to open up the actual tut9.cpp. which will contain the main. And I've just got a call in the main, so I have one main for running just stuff for examples with the actual node list, and the second one with the word lists. Right now we just have to work with the node list. Up here at the top I am going to open up the actual list.h. Oops. So our usual defs, you have the struct defining it for the type, and you have a list of all of the actual other headers for the functions that you'll see in this tutorial code. And finally, I will open up the list.cpp. Okay. In the list.cpp, you will see some extra methods, so similar to the last tutorial where there is a method called createDemoList, which will just create a linked list where it has the number of nodes you specify and the data goes from 1, 2, 3, 4, 5 or whatever all the way up to like whatever your value size is. There is also the same delete method from last time that will deallocate an entire list and set the head to null. And we have the same write list that we saw before that will go through printing out the entire list to the actual screen. Otherwise, we're coming to question 1 from the tutorial, and it says, suppose that you've got a head of type node pointer, and the head points to a correctly formatted linked list of integers. And the following code segment is intended to find the sum above this list, and like, what are the 2 things that we could see that's wrong with this code? So this is the same code that you'll see down here in the actual bottom left, right there. It's bottom right, sorry. It's the bottom right here. And we have to look at and see what's happening. And I want to step through this step by step. Okay, well this should just be an integer, sum equals to 0. That's okay. We have current equals head, and you're like, okay, well that's fine. That's what I want is a pointer that's going to move through the entire list to start here. But then we finally in this while loop have current arrow next does not equal null. Can you guys see something that potentially could be wrong with that? Well, there is an issue of what happens if the list is empty. So right here I have the sum method, and what if the list that we give it is empty? So head's null. So if head is null, current will be set to null. When we go here, current arrow next, we try to dereference that pointer, this will crash and cause a segmentation fault, which is something we saw before. So let's see if we can kind of fix that problem first. We can go to the main. So you'll see in the main here, I've set up an example where it creates list 1 is just a linked list that has 5 nodes in it. So 1, 2, 3, 4, 5. And then list 2 is empty. I then print list 1 out to the screen, and then I want to sum it up. Then I have list 2 right here, and then I try right to the screen, and then I try to sum it up as well. Now we can see for this first run with the list is it actually gets through and gives us a number. We should be validating if that's correct or not. But we can see here when we go to list 2, this is blank and it's causing a segmentation fault core dump, so it means it's crashing. So the issue here is the fact that, oh, that head is null. We can't step through this. We can't go through every single node in the actual entire list. That's an actual problem. So like if head's null, this sum should just be returning back 0, but it's causing a crash right here because we're trying to dereference a pointer before it's actually referencing any data. Now before we go on, let's also check something else. Did this actually even work for the actual expected output? Because look at these numbers. This has the nodes 1, 2, 3, 4, 5 in it. That's all the data. It's supposed to summing those up, but we got 10. Does that seem right? Like, I don't think so. Even if we go backwards, like 5 plus 4 is 9, plus 3 is 12, plus 2 is 14, plus 1 is 15. So we should have been getting 15. Well, what could be going wrong here? Well, even if we presume for a list that head isn't null and it goes in here, you have to remember that the current arrow next is actually going to be pointing and checking, oh, is the next node null, and then stopping, because we only move the pointer forwards right here. So if I switch to OneNote for a second and just draw out a quick example, is if we assume that the head is actually not null, so we have head referencing to a node. I'm just going to do a few nodes here. Let's see, that's got 1, that's got 2, that's got 3, and my usual way of drawing null there at the end. And if we start at this, we set current equals to the beginning, and then we have sum equals 0. We'll start here, and that's how it's setting up to go into the code. So go back to the code for an actual second. You see sum is 0, current equals to head. That's where our drawing is. Next is checking is while current arrow next does not equal null, then it will go into the actual code and add the sum from the current data and then move to the actual next node. So let's go back to the actual drawing. So for that first step, before going into the while loop, we check is current next equal null. So again, it's going to go to the node, access the next, and then go over here and check, okay, is it null? Over here, like, no, we're actually referencing something over here, so it is valid. It will go into the actual loop. Right here, it will then add from the current, getting the data from the current one to sum. So that is 0 plus 1, that equals 0, equals 1. Yeah, I can really add right here. So now our sum is 1. And then current then gets moved to the next one right here. And we're done that loop. And the next time it's going to go up. And now it's checking again, is current arrow next right here null? Well, no. So that's okay. The next one isn't null, so we'll go in there. It then adds 2 to the data, so from the current one that's referencing right here, and we get a result of 3. Then moves to the next node. And then finally here goes, is current arrow next null? Well, yes. Yeah, that's null. So it won't go into the actual while loop. It will not add this data 3 that's right here, and we have an incorrect actual output to the actual program. So this is the issue to remember, that with that actual section of code, we have right here is that if you're doing while current arrow next doesn't equal null, and we're doing a single linked list where the end is marked by null, then this will stop at the last node and not go into this. So we need to fix this, and it's actually like a quicker fix than you think. Right here, we'll go back down here, and what we can do instead is just go while current doesn't equal null from the code. So this goes all the way and will stop when the moving reference we have has gone off the end of the list. So if current comes in here and the list is null, well then we won't even go into this actual loop and it'll return back 0, which is fine. Otherwise it'll go through and sum everything properly. So let's compile and run it again. There we go, we got the first list, so we're not getting a core dump at all from right here. And then we are actually getting here like, okay, boom, there is the list, sum is 15, so now we're at summing properly, so we did get that last node in the list, and now when the list is empty in here, it's not crashing, and we're getting back a sum of 0. This other output that you're seeing here is then for part of the actual next question. So we're done question 1. So make sure again that you just have in the sum list method that instead of in the loop where it says current arrow next does not equal null, you change that to current does not equal null so that you will properly step through the entire list. Okay, next question is a little bit more tricky, but it's talking about, well, how would I physically swap two nodes that are in the middle of a list? So here is, suppose that we have a pointer pi and pk, and they are both pointer variables of type node pointer, which are already pointing to nodes I and k in the linked list, and both are not null, so I and k are arbitrarily counted positions, so starting from the beginning of 0, 1, 2, 3, 4 up. Write C++ code segment to swap the node at I plus 1, so the node that's after that node pi, so it follows after it, and the one that's after k. So the node that comes after p has to be swapped with the one that comes after pk. And now, although swapping the data is actually an easier way to deal with this, the challenge here is to really, how can we manipulate linked lists to get to working with these linked actual structures? Now what you can assume is that pi will always be before pk, so it won't follow like afterwards. pi and pk will not be null. And the node at I plus 1 will not be the same node as pk. So it's not like pk follows one step afterwards from actual pi. And pk will not point to the very end of the list. So this is in between the actual lists. Now what we should always do, and again most people don't want to do, is actually go and draw out some examples to visually see how this would actually work. So let's switch back to OneNote. Move up here again, and we will just draw some examples. So assume I have a list here. Give me a second to draw a few nodes. So let's assume that we picked, and so I'm going for indexes 0, 1, 2, 3, 4 up here, similar to actual arrays right here. And let's assume that we are going with I equals 0, and we have k equals 2. So what this means is that I plus 1 equals index 1, and k plus 1 equals index 3. So if I'm drawing this out also on top, this means then, okay, I've got the reference I right here, and it's referencing to that first index 0, and then I have got the reference k, so the pointer k is referencing to node at index 2 from right here. And so what I need to do is I am swapping these two nodes. So I could normally just swap the data, so put the 3 over here, and put the one, like put the 3 over here and then the 1 over here. But the challenge here is to practice and work with pointers for stuff and manipulating these. And so what we want to have resulting after this is that we have to move this entire node here over to here where this node is, and then vice versa, swapping between them. And keeping the same structure that the node that's in the beginning has to reference to node 2, that's right here, and the node that's here at index 2 has to reference to node 3. And we have to make sure that we don't lose any references. So going over here. So moving those. Now specifically this problem is saying the one that follows afterwards. So we actually have to move this node here that's index 1 over to here. And the one that is at index 3 has to pop back. So we have references to the I, we have references to the K, but the problem here is to actually move the nodes that follow after them to swap what's happening. Here. So if I was to visually draw this out, is once we've got this done, just make some more space. This is the resulting list that we'd have. So this means that 4 has moved over to this spot from right here, and then 2 has moved over to here. So swapping locations. So afterwards. And what we know so far is that we have these pointers here. So the I and the actual K to hold everything. So it holds each spot. So we know is that starting down here is this node 4 is that the I that we have here, its next has to be then pointing to node 4, and then node 4's next has to be pointing to right here, the one that follows after it. So the steps that are going to have to happen is to slowly move stuff out, so to unlink it and reset where we have some of the actual data. So I'm going to do this step by step drawing it. It may get a little confusing on the actual diagram from right here. But we know first off is, okay, let's say we're going to move this here. And moving over the node, moving forward over to back to here. Now the idea is that its next has to follow what follows after the node that's actual 1, and the node that's before it has to point to 4. Here. So what I know is I can go for its next, and then next, so going 2 nexts right there. And that will give me the node that's after that for stuff. And I can save that. So I can also say, oh, like, hey, PK, right here. And I can say, oh, this node that you have to go up to next to is that this is equal to what's there. And moving it. Now, this drawing will get a little confusing, so I'd rather go back to the actual code at this time to follow along. And you can see this is the actual method in the list. Back here, and in the list.cpp file you can go down and we've got the swap node method. So this is the one that's actually going to be doing the swap right here. So given 2 indexes, and you can see in the main I'm just giving it index 0 and then index 2 and then the list, and then swapping the actual data. In here, to actually physically get this code to write, or given a list, is I've written a get node method that you give it the index and it'll give you back the pointer. This method here is just above, which just uses a counted loop that has a counter that moves down and stops the loop when it's at the desired index, always incrementing forwards from right here, and handling special cases that if they give us an index that's negative, so we don't return back anything, and then this is here just in case they give us an index that's larger than the actual size of the list, but otherwise using this as a way to step through the entire list and then return it back. This method here gets the nodes and then just validates quickly that it follows the preconditions that we have over here for the actual node. And then goes through the couple steps right here of setting up some references for everything we need to actually do the pointers. So we first get is, okay, well, what's the node after PI? So we have PI. The one after it is the one that we actually have to swap. And we also get the node that's after that one. So we basically have 3 pointers that we are working with at this time. So let's go back to our drawing example to add those in. So we have to add in PI next, and then after PI next. So in that case for 0 is that we have PI next, which would be this one here. Which would be referencing right there. And then the one that's after PI next. Would be referencing up there. So we've got these 3 pointers, 1, 2, 3. And at this current time, in the case that example we're working with, K is also referencing this one, but we wouldn't know that for directly. We just have these 3 to be able to move. Next in the code, I set up some other pointers. So for the node after P, K, and the same thing as the node that follows after that as well. It's just setting everything so I can start doing the work. So we go back to the actual drawing. We have K, we have PK next. And after PK. So now you can see we have those 4 references. So 1, 2, 3, 4, 5, actually 6 references actually overall in total. So going back to our code, the way that lines up is there's the P reference, the reference to the first node, the reference to the PK node, and then you have the P after and everything else. So all these 6 different pointers that we actually have. And the idea is that just to have access directly and easy to read so that we can actually start manipulating and changing the links that are actually referenced. So visually, even though I know this looks chaotic, this is how we have all the actual pointers and where we can start doing the actual work. I then will go and we'll go line by line in the actual code. So you can have the code open while I do this, and I'm going to change the pen color so that you can see when I'm updating some of the references. I'll do it in blue. So the first one here is saying that the the first line of code right here is saying that the pointer that so PI, arrow next equals PK next. So we follow is the pointer at I, which is this one right here, and we're saying, oh, what's its next to? So we're following that and referencing over to the node that's right here for stuff, and then saying that it equals PK next. And remember, PK next is over here. So we are changing this next reference, following where we were originally going up there. Next, and it now references over to that node. Okay. So that's step 1 done of that line. Next we have pk next equals after pi. Oops. I have to go back and make a change. I apologize. I just realized I made a mistake in that drawing. So I've got to go back. Right here, and I made a modification to the wrong spot. I really apologize about this. But why I'm drawing, and because the drawings I can see I get it right, I've got to go back to the code, and I just realized I was following along too fast with this. But going at this first line right here, I drew that wrong from right here, what I was accessing. So we're saying pi arrow next. When I'm in here in this drawing, what that actually means is that pi, and I'm accessing this variable right there. So that is the pi arrow next equals pk next. So I apologize for that line. So it means that we are changing this reference, and we are saying it equals pk next. And this is pk next right here. So it means I'm changing this one now points to there. So this is the correct spot we have after that actual first line. So this is how we've modified the list. So we're not done yet. So I've got this right now. Go back. Now the next line is we're saying pk arrow, pk next, going to its next right here. So this is pk next. I am then accessing that reference right there. And we're saying that we're making it equal to the after pi next. So the after pi next is this one right here. So getting a little choppy in here. I mean, it equals that right there. So our list is not done yet. We still have more to go. We're then now saying that pk next equals pi next. So pk next. That's this one right here, and we're changing this, and we're making it equal to pi next. Oops. So right here, get this right, no. We're changing pk next right there equal to pi next. Referencing down. And then lastly, we have pi next right here, accessing its next variable. So we're going here, and now we're changing this one. Equals after pk next. So this is after pk next. So kind of crazy from there, But if we erase some of the other stuff we see behind here to make this clearer, then follow along with the path, you can see how we have the proper actual list now. Redraw the indexes as we go through. So we start at head, that's got actual 0 from right there. We then follow along right here to the actual 4, which that would then be index 1. We then follow conc 4 to the next one right here, that would be index 2. Follow along to here, index 3. And then lastly, index 4. So weird about that way for following through everything, but we have the right flow of this. I would suggest that you draw this out and go through the all steps to get used to this swap that happens when you're swapping two nodes that are in between. If we go back to the code in the main, you can see where you have a call to this. We're just going to do that same exact thing we did visually from right here. And we can see if we go and run this. Again, we have the first list that's up here that hasn't been changed. That is 1, 2, 3, 4, 5. And if we are swapping index the things after 0 and 1, so we'd be swapping the 2 with the 4, we should see that 1, 4, 3, 2, 5 as our output. And you can see we get that here of 1, 4, 3, 2, 5. Okay, so a little confusing, but you should try to step through this and draw everything as it's changed. So even my diagram made it kind of weird, but step through and understand each of these things that are going on and why I set up each reference there. Okay. Now, the next question here is something I'm going to leave up to you, which is to develop some actual test cases. So there has been a solution that's been posted with this tutorial, but it says develop a complete white box test plan for each of the following functions for these steps. So identify and label the branch points. Based on step 1, write down the subheadings under condition tested, and then develop test cases for each one of these. So note, these functions process linked list integers and write linked lists for input using these brackets in a similar code. And so remember, when you're doing white box testing, you're looking for each case or path that you could possibly go through. So you have one branch point here if head is null. You have another branch point coming down here where you have the else's. And then you have the loops that are right here where you could have the case where it goes into it 0, 1, or multiple times into this. And so you have to think of what are your inputs, so only using the actual head pointer and the actual value to cause this to happen. Hint I can give here is for this first one is remember that that would be value doesn't matter here at all. It could be anything for the inputs, but if head is null, it will trigger this branch point. And then after it's been done, it'll mean that there'll be a new node that's actually created based upon the value you have here in value. Everything else after here for controlling this is based upon how many nodes there are in the actual list. So a run of 0 won't actually really happen to get down to here because, you know, it's like it'll always go in that to get into this there'll be a list. There'll have to be at least one node, so you'll go through it. So you want to play with those nodes. And then you have a similar thing that you should be doing here. So again, you want to go and actually go into the tutorial solution, like step through this, trying to set it up yourself, and then look at the actual solution and validate it through that way. Instead of doing that, I wanted to spend a little bit more time and now just go through these that you see here. So there's full code solutions for all this. I want to just explain these first ones and then talk about these other ones because everything is fully coded for you as well to play around with. And so all of this code that you will see here is found in the wordlist.h and .cpp class files. So first in your main, you have, so in the toot9.cpp, just comment out node list main function and uncomment the word list main function. So you can run all of this code. And then this is a longer function down here that will run demos of everything, letting you pause as you step through each one. So in my top screen here, I'm going to open up wordlist.h. So you can see the define there, you can see the structure and the pointer, and then you have the headers for the rest of the actual methods. And then in the bottom, I'm opening up wordlist.cpp that has the rest of the code. In here, just to help visualize everything, I have created again a word creating a demo word list, and this one will create a list of your size and we'll just add words to it, but in this case I'm using sprintf and a counter, so it'll just create called word 1, word 2, word 3. So if I remake the program and run this for the first list, you can see everything that's coming out of here, calling that create word demo. So I create 4 lists, one of size 3 of size 5 and one of size 7, and you can see that there for list 1. It just populates it with strings with numbers in it. So word 1, word 2, word 3, word 4, word 5 for the rest of these. I then have also created a delete list, so go through deleting each node in that linked list properly, and then an equivalent write list to handle these word nodes. And now I'm just going to move down to the remove word function. So this one's a little different. So it said define here is define the function specified in the following prototype. So we have remove word, taking in the head of a word pointer as passed by reference, so we can modify it. And then we have the character word that we are actually searching for. And so here it says, given the head pointer of the linked list of words and a C-string target, this function removes and deallocates the node containing the first occurrence of this targeted word. If the word is not in the list, the function returns without modifying anything. And so this will happen even that we have to modify and worry about the cases if there's only one node in the list and heads pointing to that we have to delete, and we also have to set head to null. And it's going to go from the head node through the entire rest of the list to do this work. Now, to do this, you would want to break it down in 2 cases, where I like to do this just to break it down, where I find the actual word in the list first, and then I deal with actually removing that word from the actual list. So to search, we just want to set up what we usually have, which is a reference to the very beginning we have here, and then I'm also going to keep a reference or a pointer that's going to be always pointing to the node before the current one, because current will find the match of what we're looking at, and previous will have us have access to the node that's just before it. I set up a loop with current does not equal null, and then current equals next here at the bottom, so it moves and goes through every node in the actual list. While I'm searching through it, I then use the string compare, and if we get 0 back from the targeted word, I'm going to exit out of this loop knowing that current is currently pointing to the current node we're at. Otherwise, before I move current, I set previous equal to current to keep track of the previous node, and then I modify it. So I always have this kind of trailing pointer that's moving through it. After this, we have some different cases that could happen. Like 1, what if the word wasn't in the list? We would have gone through this entire list, and coming right here, current would be null. So I just exit out of the function. So if the word wasn't found, it's exit, no changes made. After that, we have some special cases to worry about of what happens if we're removing at the start of the actual list, what happens if we're removing at the end of the list, and then what happens if we're removing somewhere in the middle of the list, so modifying stuff. And the idea here is that at the start of the list, I am just actually moving the head pointer to the next node after it, because if I'm removing the first node, I have to make sure my head reference or the starting reference is now not also deleted and linked to a node that's going to be removed from the list. I have to move it to the one that's afterwards. I am then making sure for my current node that it's not linked into the actual list, and then down here at the bottom I am actually deleting it coming out of here. Next one, if we're at the end, and that's where I'm checking, so if current arrow next is equal to null, no, we're at the end of the list. So we're perfectly okay. I am just actually setting this, so arbitrarily didn't even need to deal with this, is that this should be prev arrow next is equal to null. right here, so that the end of the previous node now becomes the new end of the list. So you will have to modify that in your solution for this. So it was current, but you have to set this to prev if that has not already been modified by the time you're working on this tutorial. And then otherwise, we're removing and modifying of, okay, unlinking that the previous node links to the one that comes after the current node, and then deleting it. Okay, so let's go. And you can see here, I've got the main waiting for enter. If we come down to here, that's just this function right here waiting for me to hit enter before it goes on to my remove example. I'm just going to kill this since I had to modify the code and rerun it so that we have the newest version of the code, since I just had to make a quick change. Okay, here, and what I'm doing a remove is we're removing the word _02 from list 1. So I'm calling that remove, and you can see us printing out all of the lists. So when I hit enter, you can now see afterwards that list 1 from before had word 2 at this location right here, and then down here, boom, we're good, word 2 has been removed. Now following after this, it did ask for, question 4 here, is remove all words, but that'll come out like defining remove all words, but that was actually already done from right here. That is further up in the code, which is your delete list. So given the list, it goes through and will properly delete all of the actual code, and this is the same as the last tutorial when I talked about it. Next, what you'll find throughout the rest of these is these next ideas for practice things that you should actually write. So writing a function to determine if two lists are exactly the same, making an exact copy of a list, writing a function to remove all occurrences of a given word, and writing a function to insert a new word into a sorted list. So I have coded all of these already, and I won't go through them because we're already at 42 minutes on this tutorial. But what I suggest you do is you should try drawing it out and coding it yourself first, and then coming back to actually validate it here. So you can see an example where I code to go through for comparing if everything's the same. Then I have one for making an exact copy of a list. I have one for adding a word to the actual start, which is a helper method, one that removes all matches, and then one that does actually add sorted. And the actual main that I have here goes through a bunch of examples for that. So we can run through it quickly here, where I do detecting, okay, are the lists the actual same? So if we compare list 1 and list 2, this is list 1, this is list 2, and they're not the same. See, list 2 compared to list 3, they should be the same, the exact same data, and we did get that coming out. Here is list 2 and list 4, so they're not the same. Should be detecting that they're not the same. After this is making a copy of the list, and then I also do a case where I remove word 2 from list 2, and so we see that we have a duplicate, so this is list 2 before doing anything, this is the duplicate of it, and then I modify the actual list 2, so it removes here just to show that an exact copy has actually been made. So that's right here. I make a copy of the list, then I remove something from list 2, and I show that list 5 is not affected by the change that's done to list 2 after we've done the actual copy. Then in case of removing all matches, so from list 5 that we have here, I add some extra words into it. So we have this here with a whole bunch of words and showing that word 5 in multiple locations at the start, the end, and the actual middle. Right here, and then we have it here afterwards where it's done running. And then finally we have a case of showing you doing add sorted. So we're at 44 minutes already for this tutorial. Apologize for the few mix-ups that I've had before, but you have access to all the code, and it's good challenges for the assignment, for the midterm, and for the future actual final. It would be a good practice to try working through writing these functions on your own, or stepping through and taking a look at the actual solution that I've provided in the code. Otherwise, if you have any questions, please feel free to contact me or your current professor, and I hope just in general that you are still doing good as we reach almost the halfway point through the semester.